Hello, I'm Dr. Lorraine Tide, Director of Earth Sciences Solutions here at Esri. I will be your host for today's webinar entitled Earth Science Research Methods Protecting Our Planet. ArcGIS, the analysis ecosystem that facilitates scientific discovery. At Esri, we believe that humanity and nature can coexist and thrive. Our belief is rooted in the idea that a mutually beneficial relationship starts with respect and deep understanding of our planet. For over 50 years, Esri has helped and continues to help businesses, governments, and people change the way they lead, plan, work, and live, all in an effort to advance sustainable prosperity for all. This is strong in our culture and all that we do. We support the science community and seek to do good science as it underpins much of what we do as an organization. This also helps us evolve ArcGIS into a comprehensive geospatial analysis ecosystem that facilitates scientific discovery. With GIS, our view of our planet is shaping in front of us as decades of record multidimensional Earth observations feed our location-based technology, spatial temporal analysis, and multidimensional visualizations move us towards scientific analysis that is transforming and improving our world, making it a place where humanity and nature can not only coexist, but also thrive. As scientists, our ability to infuse our scientific knowledge into the broader fabric of society sets us on a path to achieve a more sustainable planet where prosperity exists for all. Scientists today change the world through acquiring deep knowledge of our planet. By mapping challenges and changes in Earth systems with the power of location technology, a path forward to advance sustainable prosperity for all can be achieved. It is happening around the world. COVID has led us to a geospatial awakening, an urgent call to understand and respect each other and our planet. Society, businesses, and governments alike rely on science and application knowledge using location intelligence and AI analytics to rethink where and how to solve important problems that lead us to protecting lives and property, driving economic growth, and supporting smart decision-making. The next generation of science entails where ArcGIS, rooted in location intelligence, is an innovative scientific analysis ecosystem that is open, flexible, and interoperable to support innovation. By way of reliable artificial intelligence-led spatial analysis and robust multidimensional visualization, GIS helps scientists to answer a myriad of questions about spatial patterns and what process is responsible for those patterns. ArcGIS makes science more accessible and immersible and enables open sharing of data, greater collaboration, and compelling science communication at many scales, like individual researchers, lab work groups, multidimensional analysis groups, multi-departments, multi-universities, university to agency collaborations, and citizen engagement. With ArcGIS, scientists can make a difference in society. The next generation of science entails where? When we root ourselves in the geospatial mindset, we can see from several dimensions our human-made systems alongside natural systems. We see interconnections and interdependencies. We look to spatial data for answers and direction to further our understanding of how human activities are driving fundamental changes to the Earth. Location-based knowledge provides a means to improve the quality of life without increasing the use of our natural resources beyond the Earth's capacity. For those of you new to ArcGIS, our ArcGIS Online is a complete mapping and analysis solution to get you started. For those who are well rooted in ArcGIS, you are aware of the extensive analytical capabilities across the ArcGIS platform that allows you to collaborate with your peers and work on multidimensional data sets and enhance visualizations that allow scientific discoveries to be made. There's a link here that allows you to try ArcGIS Online for 21 days to get started with geospatial analysis. Esri empowers scientists with a geospatial ecosystem of vigorous scientific discovery, transformative multidimensional analysis, and data dissemination, optimized field operations, and research communication tools. The ArcGIS ecosystem is open, flexible, and interoperable to support innovation using location to find patterns and tackle complex problems. This ecosystem is designed so scientists can spend more time doing meaningful science and less time building capacity from the ground up. Now I welcome 3 scientists to join us for 3 back-to-back demonstrations that extract deeper insight from massive volumes of multidimensional Earth observations using a comprehensive set of analytical methods and spatial algorithms, including machine learning and deep learning techniques to solve problems that face our nation and world. The first demo will be on the prediction of coral reef systems given by Dr. Aiden. The second demo will be on time series trend analysis and forecasting given by Anitka. And the third demo will be on solving the world's problems with GIS to be delivered by our own Dr. Kursky.
Hello, my name is Oren Aiden. I'm a researcher at ESRI's Spatial Statistics team. And today I will discuss spatiotemporal modeling of coral bleaching. Corals will expel the algae living in their tissues if ocean conditions are not favorable for the coral to survive. Even though the algae can come back to corals, these bleaching activities stress corals, and it can shorten their lifespan if this bleaching activity is prolonged. And today we will use spatiotemporal machine learning to understand oceanic conditions that cause bleaching so that we can make forecasts of where bleaching events are going to happen and inform conservation. The map that we're looking at contains information on coral bleaching activities recorded for the past 20 years. When we zoom in to Gulf of Mexico, we see a variety of bleaching activities. Here, red pins indicate high bleaching, meaning that a large area is bleached for an extensive period of time, whereas other colors indicate lower levels of bleaching, after which corals can safely come back to the algae. Corals can receive algae after these events. Knowing that this is spatiotemporal data, let's take a look at the time aspect. In ArcGIS Pro, we can visualize temporal information quite easily. And here we are seeing that we received more and more measurements after the year 1998. Note the higher number of counts of bleaching events after this time. This doesn't mean that coral bleaching did not occur before these days frequently. This is just a bias in our data. And in order not to bias our analysis, we will work on later years of this data starting from 1998. Another important aspect of this problem to understand is the distribution of different severities. Here, higher numbers indicate higher severities. And we see in this histogram that the distribution of severities over space and time seem to be almost uniform. So we don't have to worry about stratifying our data set. This is a multifaceted problem that will require us to integrate data from multiple sources prior to our spatiotemporal data analysis. For this reason, I will use Python notebooks inside ArcGIS Pro, and this will be the overall workflow I will follow. I will get spacetime cubes on oceanic conditions from UCAR, NOAA, and other sources. I will download these netcdfs using Python notebooks inside ArcGIS Pro. And in ArcGIS Pro, I will wrangle and get my spatiotemporal data ready, such as removing spurious readings. And after the data is ready, I will use our R integration called the R ArcGIS Bridge to create a presence-only model to understand drivers behind bleaching. In this first notebook inside Pro, I will connect to Glob Contour server and download oceanic conditions that are indicative of carbon dioxide content, which is an important indicator for coral bleaching. Once all of these netcdfs are downloaded, I'm going to join them into one spacetime cube to get it ready for my analysis. Once the spatiotemporal data source is inside ArcGIS Pro, the story doesn't end there. The next step I will need to take is to wrangle this data so that I can use in my analysis. When we look at the spacetime cube data that we've downloaded in ocean conditions, it is obtained at ship tracks, so it is spatially discrete. I need spatially continuous surfaces so that I can model ocean conditions where bleaching is observed. For this reason, I will first summarize the spatiotemporal data. As you see that this spacetime cube contains a wide variety of data sources, and I will need all of these data sources, and I will summarize them with certain statistics, such as the mean, standard deviation, and minimum and maximum within a given time range. Since I'm doing this analysis yearly, I'll be creating statistics for every year. And after this is done, I need to create an interpolated surface. And I will do so using empirical Bayesian kriging that can account for non-stationarity in this data set. And the resulting average salinity, for example, from the spacetime cube will look like this. Of course, I need to do this for 10 different variables I have for a 22-year time span for 6 different statistics. We need to automate this. We need to automate these 2 tools that I ran. And again, using Python notebooks in ArcGIS Pro, I can easily do that. I can wrangle my data set. I can aggregate time series annually. I can create my interpolation surfaces using empirical Bayesian kriging to realize this workflow on big data and to repeat this so that I can create my exploratory variables. At this point in my workflow, we have all the data that is available to us, the oceanic data that is wrangled and ready to be used. The next step is using the max-ant model for presence-only modeling of bleaching. This way, we can understand conditions that are more conducive to bleaching. Let's switch over to an R notebook. After we import all of our libraries, such as ArcGIS binding, which is our ArcGIS bridge integration, we can interact with all the spatiotemporal data sources that we have prepared in ArcGIS Pro. Firstly, I will bring in ArcPy, which is a Python library that ships with Pro, and this is our spatial machine learning library in R, so that I can utilize R libraries from Python libraries from R. Next step is bringing in bleaching data into R as an R data frame. And after I bring this data set in, I can leverage the full power of R and all the libraries that are available to me. And as you know, there are more than 12,000 libraries available in R for me to do analysis with. But today, I'm going to be using a specific library called MaxNet. So the first step that I will complete in R is extract rasters that I just created in Pro at bleaching location and mask them to the shallow parts of the oceans where I would expect bleaching to occur. We will do this using a geoprocessing function that is in Python in ArcPy library. But since I've imported ArcPy into R, using the rbridge function, I can easily run this function in a loop and extract masks for shallow bathymetry from all of my predictor rasters. So I can drive Python analysis from R. The next step is using Living Atlas data. I have another data source that I cannot obtain anywhere else but the Living Atlas. It's called the aragonite content, which is an indicator for acidification. I can directly access this remote geospatial data source from this REST API and bring it in as an R data frame using the R bridge. And after I bring in aragonite, I have my full set of rasters ready for analysis for my presence-only modeling. And here are all of the wrangled rasters for the year 1998 that is ready for my spatiotemporal presence-only model. Now I will create a presence-only model for bleaching using MaxNet. MaxNet method implements the MaxN methodology that defines how are locations where bleaching is observed different than background locations, which are shallow bathymetric locations where corals are expected to be observed. This method will find relationships, data ranges in all of my rasters that define events that resulted in occurrence of bleaching. After I fit this model, here is the probability of bleaching event to occur given my environmental rasters. You will see that quite a high number of locations, about 40% of our data set, has quite a high likelihood to have severe bleaching events. And after I create my prediction raster for every year, I'm going to export it in raster format in ArcGIS so that I can use it for further spatial analysis. I will take one more step to compare the model I just created, make a forecast, and find its validity. To do that, I will bring in NOAA's Coral Reef Watch feature service, which is again a REST API, directly as an R data frame. This is quite simple to do with the R bridge so that my data is in R data frame format. And again, using our leaflet integration, I'm going to create an interactive map of bleaching events in ArcGIS Pro so that I can interact with this data set and look at the latest bleaching events recorded by NOAA's Coral Reef Watch. And I'm going to overlay the raster of my predictions on top of this to validate if the locations I predict to have high bleaching severity corresponds to observations. I see that in this raster, high probability of high bleaching severity corresponds to areas of recorded high bleaching events. And this gives me confidence in the model that I use. Similarly, when I zoom over to Red Sea, areas where I find low probability of high bleaching severity corresponds to areas with no bleaching recorded at these measurement stations. So with this being said, I can create this complex, sophisticated spatiotemporal workflow to understand the patterns behind coral bleaching, leveraging ArcGIS, Python, and R to realize a large spatiotemporal data science workflow. Thank you.
Hi, everyone. I am Ankita Bakshi, and I am a product engineer on the spatial statistics team at Esri Redlands. Today, I'm going to talk about climate change and how sophisticated methods are the need of the hour to understand its impacts. So here I am taking this opportunity to draw your attention to the increasing wildfires in the state of California in this era of climate change. To begin with, on this map, we are seeing the Cooperative Observer Program, or COOP stations, which collect daily weather information throughout the state. And I'd like to thank NCAR and UCAR for providing the daily maximum temperature and precipitation values recorded at these stations from 1950 to 2004. The data was shared in a NetCDF format, which is common for such type of multidimensional scientific data. So step one was to take these NetCDF and create feature layers with maximum daily precipitation and temperature values using the Make NetCDF feature layer tool. The resulting layers each contain about 13 million daily observations for a period of 54 years. To understand the patterns in precipitation and temperature values, step two was to take these daily observations and aggregate them annually in a spacetime cube. The Create Spacetime Cube from Defined Locations tool lets me specify the temporal extent at which I want to aggregate my data. And in this case, I want to aggregate my data annually. And by simply putting the spacetime cube in 3D, we start seeing some obvious spatial patterns. For instance, the coastal areas have lower maximum daily temperatures than the inland regions. However, to understand how the values have changed over time, in step 3, I used Visualize Spacetime Cube in 2D tool and its trend analysis option, which runs Kendall statistics at each location to find significant trends in the data. The darker purple locations show an overall upward trend in the maximum daily temperature values, and the darker green locations show an overall downward trend in the maximum daily temperature values. And when I add California fire perimeters to this map, we start seeing co-location between the wildfire areas and the areas that are experiencing increase in temperature values. And when I add precipitation to this equation, we can see that these places are in fact getting hotter and drier, making a perfect recipe for wildfires in the state. These trend analyses really help us understand and uncover the patterns that are historic in nature, the historical patterns in your data. However, what I'm excited to show you next is a new set of capabilities that lets us predict into the future. In ArcGIS Pro 2.6, we introduced a whole new toolset for time series forecasting, ranging from some more traditional modeling methods like curve fit to more sophisticated machine learning-based approach like forest-based forecast and exponential smoothing forecast. Let's look at curve fit forecast. The curve fit forecast fits these parametric curves to your data and forecast future values. For my input spacetime cube, I aggregated my data monthly to capture those subtleties in monthly temperature values. I'm going to forecast for the next 24 months and let the tool auto-detect the best curve type out of linear, parabolic, exponential, and S-shaped compass curve for each location. One of the parameters that you will see in all of these forecasting tools are these number of time steps to exclude for validation parameters. In time series forecasting or in any type of forecasting tools, it is critical to know how well of a forecasting job your tool did. And that can be computed by comparing the forecasted values to the raw values. And this type of validation is just built into the tool. The output of my curve fit model symbolizes the last time step that was forecasted, which is the 24th month in this case. But one of the most important and my favorite outputs are these pop-up charts that the tool automatically creates. So for each location, when I click around, the blue points represent the actual temperature values, while the forecasted values are shown in orange. As you can see, a simple curve fit model didn't do a great job of capturing the complex patterns in the data. I'm going to use another tool, which is exponential smoothing forecast, which is recommended for such data which has trends and seasons. And again, I'm going to forecast the next 24 months. And since this tool is recommended for seasonal data, you can specify the season length here. But if you don't know what the season length is in your data, or if different locations have different season lengths, you can also leave this parameter blank and let the tool detect season length for each location individually. The output of this tool, if I click around, you can see was able to capture the complex trends and cyclical patterns in the data and forecasted the values in orange with a confidence interval around it. The tool was also able to detect 12 months as a season length for this data, which makes perfect sense for a monthly aggregated temperature values dataset. I also ran forest-based forecast, which under the hood uses a machine learning algorithm called random forest to train the model and predict the future values. And if I look at the output of this tool, again, I can see that the tool was able to capture the complex trends and patterns in the data set. But how do I know which model did a better job? Did exponential smoothing work better for some locations while forest-based worked better for some locations? And in trend analysis, we saw how different locations had different upward and downward trend. So it's possible that a single forecast model did not work for all the locations. So how do I know which model fit best for each location? The answer to that question leads me to this another awesome capability in this tool set to evaluate forecasts by locations. So I took forest-based, curve-fit, and exponential smoothing forecast results and fed them into this tool to find out the results location by location. And in the output, we can see that exponential smoothing model was chosen for many locations in Southern California, and forest-based did a better job for the rest of the state. Even though time series forecasting isn't explicitly spatial, as a geographer, it is so fascinating to be able to map these hybrid model results. And just by looking at which model gets chosen for each location, you start seeing some spatial patterns in your data. And as we model and forecast the weather conditions into the future, it could help us with a better understanding of what fire risk might look like in California. As an impact of climate change, the weather we are experiencing is changing dramatically. The norms that we're used to are quickly fading away. So we need to be able to have these sophisticated methods in order to detect and predict these patterns into the future. Thank you.
Joseph Kursky here on the ESRI Education Industry Team to talk with you about earth science research methods protecting our planet, applying geographic thinking to address scientific challenges. Climate, water quality and quantity, human health, natural hazards, energy. All of these issues facing our world are interdisciplinary, they're complex, they're spatial problems solvable through the use of geographic information systems, or GIS technology, and applied spatial thinking. The underlying rationale of applied spatial thinking is that only through a clear understanding of the relevant societal, physical, and natural human systems can humans resolve these challenges. All of these challenges share things. They all occur somewhere. They have specific spatial patterns, relationships, and trends that can be best understood through spatial thinking through GIS. Indeed, our ESRI theme at this year's AGU conference is Next Generation Science Entails Where? And thus, the overall topic of this is Earth Science Research Methods Protecting Our Planet. Perfect. The subtitle of the Applied Geography Journal encapsulates this notion, I think, putting the world's human and physical resource problems in a geographical perspective. Now, Paccione, 1999, defined it as the application of geographic knowledge and skills to the resolution of social, economic, and environmental problems. Paccione also suggested that applied approaches are either studies of a specific problem occurring over a small area, tracing the diffusion, for example, of pollutants through a water channel, or studies of a major issue occurring over a larger region, such as ways to model climate change and the implications of these models. He advocated a deep DEEP procedure: description, explanation, evaluation, prescription, implementation, and monitoring. Now, all of these challenges occur at specific scales. They are interconnected in and change over time and space. They all affect human populations and are in turn affected by human populations. As time passes, these issues grow in complexity and in some cases severity, unfortunately. And as the world becomes increasingly connected, socially and economically, these issues increasingly impact people's everyday lives. As recognition of these issues grows, as awareness of environmental and related issues grows, and as more people regularly use tools created by GI scientists, such as web-based mapping tools, the problems and issues to which geography or spatial thinking is applied grows with each passing year. For example, GIS and spatial thinking are applied to determine how governments should make energy and trade agreements, and how to build resilient communities in the face of wildfires, earthquakes, tornadoes, floods, and hurricanes. Addressing the complex issues regarding these topics that I've talked with you about today requires spatial thinking. What is spatial thinking? My own definition of spatial thinking is identifying, analyzing, and understanding the location, scale, patterns, and trends of the geographic, so space, and temporal, so time, relationships among data, phenomena, and issues. The NRC, National Research Council, published a report entitled Learning to Think Spatially, which made a strong case for the value of spatial thinking to be taught at all levels throughout the educational system and as many disciplines as possible. That is the goal of the Esri education program, by the way, deeper and wider application of spatial thinking through GIS so that students can be wiser decision makers and change makers in society upon graduation. Hence, we work with primary and secondary schools, after-school programs, libraries, museums, community colleges, technical colleges, tribal colleges, universities, lifelong learning to support the rigorous use of GIS throughout their courses and programs. One example of the recognition of the applied nature of geography has been the establishment of the Office of the Geographer at the U.S. State Department during the early 20th century. GIS is now nearly 60 years old. Worldwide, 350,000 organizations, including 2/3 of Fortune 500 companies, apply geography using Esri technology on a regular basis. The application areas continue to spread. For example, city planning, natural resource management during the 1980s to just about every major field by our current century, including public safety, natural hazards, human health, water quality, energy, and human behavior. The advent of WebGIS, open data portals and policies, and easy-to-use crowdsourceable field apps have opened GIS to many disciplines. I'm really quite excited about this. Business, health, data science, to be naming 3 of them. But the most important spatial tool, folks, is this one right here, your brain. This is the one you need to nurture. The tools will change, the data will change, but I encourage each of you listening to this to actively pursue spatial thinking through GIS and remote sensing. Hence, I advise you to keep the geographic inquiry method at the forefront. Ask a geographic question, acquire data and information, assess its quality, use my Spatial Reserves data, book, and blog to help guide you. Explore and analyze the data temporally and spatially. Then, act on it. Great if you study water quality with Survey 123, ArcGIS Online, and ArcGIS Pro, for example. But what can you do about it? What can you do about that issue in your community? Presentation to your city council, set up an ArcGIS hub to gain community stakeholders, for example. All these are good methods, but acting on what you've learned is important here. This leads to additional questions, and this geographic inquiry cycle continues. Be sure to communicate your findings via story maps and other web mapping applications. This is an increasingly common workflow that is increasing awareness and helping change hearts and minds. We need to consider such questions as, who decides what is useful? What are the criteria for deciding what is useful? Which is related to values and ultimately to cultural considerations. It also is keenly tied to ethics. Even how one symbolizes and classifies data on maps is value-laden and needs to be thoughtfully taught and thoughtfully done. All of these issues that we've been chatting about, natural hazards, energy, climate, water, are interdisciplinary, complex spatial problems that are solvable through the use of geographic information systems, technology, and methods. Doing so requires spatial thinking to be taught at all levels and in all disciplines throughout the educational system, and applying spatial thinking, mapping principles, and the geographic inquiry method.
2020 has been a challenging year for many. We have seen how geographic spatial thinking and geographic technology are addressing the world's most complex problems from local to global scale, especially including those in health. This special section of resources highlights the heroic response of the GIS community to the global outbreak of COVID-19, the first global pandemic of the information age, and the opportunity it presents to define trends, fears, and hopes on a daily basis. The link provided here highlights many of the GIS scientific analysis that provide answers that helped us to respond during this pandemic. Please take the opportunity to check out these resources. We would like to thank you so much for joining us to learn about earth science research methods. We will now take any questions that you have. We've had a few questions coming through in the chat, and so we have been taking those and answering them as they come through. Just going to take a look and see if there are any more that we did not get to. We've also placed in the link some links to our Jupyter notebooks. We have a fair number of new notebooks that are available for other users to take advantage of, and so please check out that link. I should also say thank you so much for joining. It's a pleasure to be able to reach you today. I know everybody's busy. I hope that you are enjoying AGU. We certainly are. We look forward to learning more about what you are doing and making a difference in the world. I don't see any more questions coming in, so perhaps we can finish.